All right, we're starting a new chapter today. Chapter 5. We're going to look at one-to-one functions and then logarithmic and exponential functions. Why do they go together? Is because they're inverses of each other. Do y'all remember stuff from algebra about logarithms? Yeah, so these are really straightforward type of sections. And then we'll jump into the trig functions next week. So when we say one-to-one functions, what does that mean? What do you think one-to-one function means? I mean cancels out.
Like just like they equal to each other,
No. No.
correspondence.
Oh, yes. So what's a correspondence? And there's a reason they use the word correspondence. Think of the old days when people wrote, what does correspondence mean in the old days? Yeah, exactly. That's why they call it that, is because when you have mail and you mail to somebody, does that go to more than one person? No. Each letter you send out goes to one and only one person. One, and one-to-one. So from each X value, each input relates to one and only one output. We'll use this symbol instead. Each value of X corresponds to one and only one value of Y. And we'll look at a couple ways. Look at it as mappings, as set points, and as functions and graphs. These are called mappings. We have set A and set B. This is the domain, and this is the range. So correspondence is each value in the domain maps to one and only one value in the range. So that's a correspondence. That's a one-to-one function. Is that a one-to-one function? Why?
Each one is going to exactly one point.
Right. Each of the domain is going to one and only one of the range. All three of them go to the same value. Is that a one-to-one? ¿Por qué no? Right. Because C sends the same letter to two different people. You can't do that. Not a one-to-one function. Pretty straightforward. Now, with that description there, points here. So let's just define it. Let's define it. Definition of one-to-one. A function f of x is one-to-one if any two different inputs of the domain corresponds to two different outputs in the range a function is one-to-one if any two different inputs of the domain correspond to two different outputs in the range. What is that? How is that different from one-to-one? How does this differ from one-to-one? Because it says if any two different inputs from the domain correspond to two different outputs in the range. Because if basically it's this.
How does it differ from what?
If I only had one element, if I had one input goes to one output, is there anything different there? Is that anything but one-to-one? The problem occurs when you have more than one input to more than one outputs. That's an example of a one-to-one correspondence because they automatically go to different. And how would you put this in words in X and Y values?
For a one-to-one function, the functions whose graph doesn't cross over itself more than once along the x-axis. Kind of.
We haven't really said cross over itself. How does it mean cross over itself?
It doesn't pass the vertical line test.
What does a vertical line test do?
It tests to see if anywhere along the input, if it has more than one output.
Okay, now, and that defines a function, not really one-to-one. For one-to-oneness, I'm glad you said that. It's the horizontal line test.
So what if you're
All the vertical line test is it a function? If it's not a function, we don't have to worry about the one-to-oneness. So that just whether we go any further, because you notice it says the first part, a function. It has to be a function, has to pass the vertical line test. Now, if it passes the vertical line test, then can it pass this horizontal line test, which is the same thing, but horizontally. It can't cross it more than once.
Does you have an equation y equals 1? Is that a one-to-one function?
Yes.
Okay.
Because for every value X you put in there, for every X value you put in there, is that X happening more than once? No, so it passes it there. In other words, can the graph is there at 1? Is there more than one Y value? No. So, and basically that's what you're looking at is when if I give you a set of numbers, that's what I'm looking for the example of the set of numbers. If I give you a set of numbers like this, Is that 1-to-1? What did you use to determine that?
Y values are different.
Nope. All the X values are different. If the X values are different, automatically it's 1-to-1. Automatically. Is that 1-to-1? What did I just say up here? If all X values are what? Different. Then it is 1-to-1. Is this one 1-to-1? Yes, because all the X values are different. Is this 1-to-1? Why?
They're all different except for the first one and last one, but they're essentially the same point.
Right. Since you only have two X's that are the same, as long as the Y values are the same, they're the same point. Doesn't matter. So yes, this is 1-to-1. The only problem comes in if you have the same X but different Ys. That's the problem. So not 1-to-1 if same X value but different Y values. Um, Is this 1-to-1? It just says, for each of the function, use the graph to determine whether the function is 1-to-1. Why not?
That's a horizontal like this.
What does this graph look like?
Forever.
Not 1-to-1 because it fails a horizontal line test. How about that one? What does that one look like? It's an ever increasing function. What are the other examples? I thought I had a whole bunch more than this. Oh well. Theorem. A function that is increasing on an interval I is 1-to-1 on I. A function that is increasing on an interval I is 1-to-1 on that interval I. It sounds like common sense. Why is that true?
Um,
What is It says a function that is increasing. What does an increasing function look like? Yeah, like the x cubed function. It's always increasing. So does it pass the horizontal line test? Yes, so it's automatically 1-to-1. A function that is decreasing on an interval I is 1-to-1 on I. Same reasoning. As long as it's continuously decreasing. With respect to the difference quotient, how do we prove that? How do we prove that a function is decreasing using the difference quotient? What does the difference quotient find? Right. It finds a slope. So if it's always decreasing, that means these 2 points, the y value, as x gets larger, the y values are decreasing. Hence, that's making it negative. How about an inverse function? What is an inverse function and how do we prove it? You've seen them before, you've played with them in algebra, I hope. What notation do we use to indicate an inverse function? To -1, yeah. And not a negative, it has to be -1, which says that that's an inverse. How do we find the inverse? Let's say that f of x is equal to 2x minus 3. How do we find the inverse?
All under one.
What this equals. So there's your function. So first thing we do is switch x and y. Solve for y, which is your inverse. So my inverse function is x plus 3/2. And this is the crux of the whole thing. If I give you a bunch of points, how do you find the inverse of that function? Let me see the example example we had a second ago with these points. Everybody finish this? The example we had earlier, I gave you these points. -2, 6, -1, 3, 0, 2, 1, 5, 2, 8. these are the points of my function, f of x. What would be the corresponding points to my inverse function? Nope. Yeah, it's like the instruction said, first thing you do is switch x and y.
Oh,
Right. So that's the only thing we have between the inverse and, so how do we prove that they're inverses of each other? If we have two functions, two x minus three, and the inverse of the function we said was, how do we prove they're inverses of each other? No.
you switch X and Y and solve for Y, and you get the second equation.
Okay, we know they're inverses because they're symmetric about the line y equals x. So if we had this equation, its inverse would be that. Because you switch x and y values. Remember these functions? If you do a composite function with the f and the inverse of f, then the resulting function should be just x. So let's look at this first one. F of f inverse of x. What that really means is the f of f inverse of x. So this one says, I take the inverse, make it my input. So I take this inverse, and anywhere I see an x, I plug it in there. So I'll work this one out. The 2's cancel, gives me x plus 3 minus 3. The 3's cancel, which leaves me with x. That's how we prove that they're inverses of each other.
So it should just be x, not x plus one.
It'd just be x by itself because it has to, the end result would be, if I took both of those equations and put them on top of each other, it's that line it's symmetric about. It's just x itself. Yeah, if you have a plus one, then we have some issues. Now, how does this help us with what we're talking about here with one-to-one function and correspondence? How do we relate to them? It has to be a function, check. Means you pass the vertical line test. If it's one-to-one function, if f of x is one-to-one, and it has an inverse, then the inverse function has to be what? One-to-one also. If f of x is one-to-one, then the inverse of x is one-to-one. It's interesting because it matches the resulting vector, the function is x. It passes the horizontal and vertical line tests. Yeah, the graphs are simply just reverse the X and Y. We just talked about that. Here's some examples.
What about when you have, like, for example, we just want to cover it, A to one, B to two, C to this, that'd be 1 to 1. But then the inverse would be, would it be?
Well, yeah, but those didn't really define a function. Those are just point, yeah, a very excellent point. Those are simply points that were just chosen out of, yes, okay, I'll use that. But yeah, but the function first, those points in the function, if it comes from a function that has to be 1 to 1, then the inverse of it will be also -1. F of X is equal to X cubed. The inverse is equal to the cube root of X. Prove that they're inverses. Verify their inverseness. One way of doing it, take this function, plug it inside here. So the cube root of X cubed, these cancel, so we're left with X. Then try the other way. Take this and put it in place of there. Cube root of X cubed, they cancel. Okay, I did a lot of hand waving there. Why is this true? Why does this become X? How do we prove that mathematically? It has to do with this conversion factor. So X, the cube root of X is the same thing as X to the power 1/3 to the power 3. Whenever you have a power to a power, you multiply. Same thing here. So we have X cubed, since it's inside there, it's to the power 1/3. Power to a power you multiply, so it's 3/3. That's how you prove it. Verify that. These are inverses. This just looks ugly. Both of them?
Plug the left one into the right one.
So take this, put it in place of X. So I have 1/(1) X.
Plus 1 minus 1. The ones cancel out. And then take the reciprocal of 1x, multiply it by 1, and you'll get x over 1 equals x.
That's the first part. We do the same thing. Take this, put it in place of there. This is 1/1. So I take the top of the top fraction, leave it alone, flip the bottom. So this becomes x minus 1 plus 1. It just looks ugly. Pretty straightforward. Let's build up the suspense and make it more difficult. Here's the function. Let me put it on pause for y'all. All right, to find the inverse, the first thing you have to do is what? First thing you have to do is switch x and y. That's step 1. Step 2 is solve for y. So we have to get rid of the fraction. Whenever you have fractions and equal sign, get rid of those. So we multiply both sides by y minus 1. So we have xy minus x equals 2y plus 1. Because we have to do what? We have to get all the y's together, don't we? Subtract 2y from both sides. And also get rid of this one. How? Add an x to both sides. So we have an xy minus 2y equals x plus 1. No. Factor out of y. Now we can divide by x minus 2. So my inverse function is x plus 1, x minus 2. How many of y'all were close? I was kind of hoping, I'm almost there. Granted, yes. If you see, I mean, it's after you look at it, oh, that's easy. But you're right. When you first look at it, it said, how do you start? You have x's and y's everywhere. So, so the first thing, get rid of fractions. Always get rid of fractions.
No, he's gonna only give us a limited time before you start doing it, so I'm not trying to.
That's a good save of not doing it. All right, so that's it for that section. Pretty easy, eh? Now we're gonna start talking about logarithms.